Hello everyone. It is a great pleasure to welcome you to our first step of learning the course Physics for Engineers. With the crisis that we are facing today, it is more important not to stop learning. So this is the new normal. Yes, we find it hard, just as hard it seems for you. But your desire to learn motivates us to strategize the learning mode suitable in our times. Though it is definitely not perfect, we let you know that we're here to teach and to listen while maintaining COVID-19 safety protocols. Now prepare yourself, clear your mind, and concentrate. Check your learning materials. Sharpen your pencil. Make sure your calculator has plenty of juice, I mean power, because we will do a lot of calculations. And of course your writing pad or notebook. These materials from the old normal should not be left behind. So keep them always in your bag, just like pretending you were going to school. Now before we begin our discussion, it is expected that you have already learned, during your senior high school days, the basics of physics such as scalars and vectors, algebra, geometry, trigonometry, and calculus. So you better brush up with these topics. So without further ado, let us begin. This first unit deals with motion. Motion is the progressive change of position of a body. Each object in the universe moves relatively with one another. A body which is moving to one observer may be at rest as seen by the other observer. When the relative distance between the object and observer is changing, then motion can be observed. The two objects are at rest, or no motion, when there is no relative change in distance between them. To illustrate this, consider a stop sign and an athlete. Initially, at a particular time, the athlete is 10 meters away from the stop sign. If he gets closer to the stop sign, let's say his distance becomes 5 meters, therefore we can say that motion takes place between them. The phenomenon of motion can be learned by studying kinematics, a branch of mechanics that deals with the description of motion of bodies. It involves various physical quantities such as position, distance, displacement, time, speed, velocity, and acceleration. These quantities are actually related to other quantities such as force, work and power, which will be discussed in Unit 2. The position, x or y, of a body is defined in terms of a frame of reference. It is our choice of coordinate x's that defines a starting point, or origin, for describing motion or any other quantity. For one-dimensional motion, frame of reference may be either x or y-axis. Horizontal motion uses x-axis while vertical motion uses y-axis. Projectile motion, a two-dimensional type of motion, uses both axes in describing position. Now let us distinguish displacement from distance. Once motion takes place in a body, its position has changed. This change in position is described by the quantity called displacement. In one-dimensional motion, displacement is denoted by delta x, for horizontal motion, and delta y for vertical motion. Mathematically, it is the difference between the final position of the body x sub f and its initial position x sub I. For instance, a car moves horizontal, changes its position relative from the stop sign, which is the chosen arbitrary origin, from 10 meters to 22 meters. If we apply the formula, its displacement is 22 meters minus 10 meters, which is equal to positive 12 meters. Take note that displacement is always final position minus the initial position, never the reverse. Displacement is a vector quantity, so it has both magnitude and direction. For one-dimensional motion, the sign dictates the direction of displacement. Since our answer is a positive value, therefore the car moves to the right or towards positive axis relative to stop sign. For vertical motion, displacement delta y is expressed as y sub f minus y sub I. Displacement is independent on the actual path of the body. To explain this, consider again the athlete that can run on different routes of the track. His goal is to run from his current position to the other end. To do this, he may run on the upper route. He can also even go the lower route. Either the case, he reached his destination. So here is the athlete's displacement. It depends only on the initial position and final position. It is a straight line segment directed from initial position, or starting point, to final position, or end point, regardless of the path the body moved. On the other hand, distance d is the total length of the path a body actually traveled. Now let us do some solving problems about displacement and distance. Problem number 1. In the figure below, a car moves horizontally, that is along x-axis. The position of the car at each point are indicated by letters. What is the displacement and distance traveled by the car from point A to point B? From point C to point D? From point D to point F? From point A to point E? From point B to point G? And from point F to point G? Now let us establish the given information. Referring to the figure, we see the position of the car x at indicated points. At point A, 0. At point B, 30 meters. At point C, 50 meters. Then after reaching 50 meters, momentarily the car has stopped and started to move backwards. Now at point D the position of the car is 40 meters. At point E, the car has returned to starting point, therefore its position is again 0. It continuously moves backward to point F, at negative 30 meters. And lastly to negative 50 meters at point G. Now we investigate the required quantities, take a look again with problem. So we make a list of these below. Now I will show you the solution. Please listen carefully. For displacement delta x, we simply get the difference between the final position x sub f and the initial position x sub I. So from point A to point B, the displacement is x sub b minus x sub a, that is 30 meters minus 0. So the answer is positive 30 meters. For the distance traveled by the car, we see in the figure that it has traveled 30 meters. Take note that the sign indicates the direction of the car. Positive sign indicates that the car moves to the right from point A to point B. We also note that the displacement and distance are numerically equal since the direction of the car from point A to point B does not change. I hope you can still follow. For displacement from point C to point D, that is x sub d minus x sub c. Then substituting the values 40 meters minus 50 meters will give negative 10 meters. The negative sign here indicates that the car moves to the left from point C to point D. For the distance traveled, it is simply 10 meters. Note that distance is a scalar quantity. It has no direction and it only measures the length of path. By the way, before we continue, I suggest you take down important notes while listening. You can also read the module provided in PDF format for better understanding. Now let's move on. For displacement from point D to point F, it is x sub f minus x sub d. Numerically, negative 30 meters minus 40 meters, gives negative 70 meters. Again, the negative sign indicates that the car moves to the left from D to F. For the distance traveled, you see in the figure that it has traveled 40 meters from D to E, then another 30 meters from point D to point F. So the total is 70 meters. Now if we take a look on the figure, the positions of the car at points A and E are the same and that is 0, therefore the displacement is 0. Remember that a 0 displacement means that the object returns to initial or original position. However, the distance traveled is not 0 because the car has traveled 50 meters from it to C, then another 50 meters from C to E. Hence, the total distance traveled from point A to point E is 100 meters. So let's keep up. For displacement from point B to point G, subtracting x sub b from x sub g, that is negative 50 meters minus 30 meters gives negative 80 meters. Again, the car seems to move to the left from points B to G. For the distance traveled, before going to point G, it has traveled 20 meters from B to C, 50 meters from C to E and another 50 meters from E to G. So the total is 120 meters. I hope that at this moment you can now distinguish between distance and displacement. Displacement only depends entirely on the initial and final positions of the object, while distance is a path-dependent kinematic quantity. We're almost done. The last item would be the displacement and distance from point F to point G. The displacement between these points is x sub g minus x sub f, which is equal to negative 50 meters minus negative 30 meters. So the answer is negative 20 meters. This item may be a tricky one. Take note the initial position is a negative value. Its sign should not be mistakenly replaced by the minus sign at the middle. So watch out for this. For the distance, obviously from the figure it is 20 meters. Well, that's it. Any questions so far? If so, kindly communicate with your teacher. Hello. Welcome back. I hope you successfully answered your first exercise. You may collaborate with your classmate to compare your answers with them. Somehow, it will give you the confidence with your answers before submitting it to your teacher. Now let us move on to another two important quantities, speed and velocity, which is much related to displacement and distance. To describe how fast a body moves, average speed is computed. Average speed, denoted by letter S, is the distance a body moves in a given unit of time. Regardless of different paths traveled by a body, total distance d, or path length, are measured and divided to the total time elapsed, or time interval, delta t. Mathematically, it is expressed as s equals distance d divided by the time interval delta t. Distance traveled and time interval are always positive values, so as with speed. The SI unit of speed is meter per second. Other units are kilometers per hour, or kph, feet per minutes, or fpm, and miles per hour, or mph. The magnitude of speed varies with the ability of the object to move. A man can walk at an average speed of 1 meter per second, while a car can travel as much as 25 meters per second. Modern cruise ships can travel on waters about 30 knots, or 55 kph. Modern airplanes and jet planes can travel as much as the speed of sound, that is around 300 meters per second. Mach is a unit used to measure the speed of these vehicles. A Mach means a speed equivalent to the speed of sound. Mach 2 represents a speed twice that of sound. The Earth's equator is actually moving at around 460 meters per second. Now before we define velocity and distinguish it with speed, I will give you one easy problem about speed. Problem number 2. In the figure below, a car has traveled a distance of 60 meters on the indicated path in 3 seconds. What is the average speed of the car? Establishing given information based on problem statement will give a distance traveled of 60 meters and a time interval of 3 seconds. For the required quantity, we need to solve for the average speed s. Then we solve this using the formula of speed s equal distance d divided by the time interval delta t. Substituting the given information. So the average speed of the car is 20 meters per second. You find it easy? I told you. But take note, this is only the average speed of the car. If we are asked to solve for the maximum speed of the car, well, we do not have enough given information to solve it. But we will investigate this one once we discuss the concept of instantaneous velocity and instantaneous speed. Now we're moving to velocity, which is sometimes synonymously compared to speed. Average velocity, denoted by v sub a v e, is time rate at which the displacement occurs. Mathematically, velocity is expressed as delta x over delta t, wherein displacement delta x is equal to final position x sub f minus the initial position x sub I, and delta t is equal to final time t sub f minus the initial time t sub I. You make some adjustment on the formula when you are dealing with vertical motion. To comprehend these things, let's say we have a car that moves along horizontal road or along x-axis. The average velocity of the car can be described. First, we set an arbitrary origin, say the stop sign, in order to describe car's position at any point in time. So let's say at initial time t sub I, which is 0, the car is initial 10 meters from the stop sign. Then, the car moves and reached the final position 20 meters 2 seconds later. So the car's displacement is positive 10 meters for a time interval of 2 seconds. Hence the average velocity of the car, which is delta x over delta t, is positive 5 meters per second. The value sign of the velocity depends on the sign of the displacement. Although displacement can be a positive value or a negative value, time interval is always a positive value. Furthermore, the direction of the velocity is the same as the direction of the displacement. For one-dimensional motion, it is sufficient to use positive or negative for directions. The c unit of velocity is meter per second, but customary units such as feet per second, centimeter per second, kilometer per hour and others may be used. Since speed and velocity are synonymous with each other, it is important to note that the magnitude of velocity may be equal or less than the numerical value of speed. First, if the magnitude of displacement is less than the total distance traveled by a body, the magnitude of the velocity is less than speed's magnitude. To explain this, let's say we have a car which traveled 100 meters along the indicated path in 5 seconds. The average speed of the car is 20 meters per second. Now we see that the magnitude of displacement is definitely less than 100 meters, let's say 30 meters. With this value, magnitude of its velocity is 6 meters per second, which is less than the value of speed 20 meters per second. Secondly, for one-dimensional motion, the magnitude of displacement and distance are equal, and therefore the magnitude of velocity and speed are also equal. Lastly, velocity is 0 when the body returns from starting point while its speed is greater than 0. Maybe it's about time to solve another problem. Problem number 3. The figure below shows the position x of the car as a function of time t. Find the average velocity and average speed of the car in figure below between time interval 0 seconds to 12 seconds. Given information are: at initial time 0 second, the position is 0. At time 12 seconds, the car's position x sub f is negative 30 meters. So again we are asked to solve for the car's average velocity and average speed in this time interval. Solution: for average velocity, we use the formula delta x over delta t. Substituting the values, negative 30 meters minus 0 over 12 seconds minus 0, will give an average velocity of negative 2.5 meters per second. Note that the negative value of velocity means that the car moves to the left or towards x-axis during the 12 seconds time interval. For average speed, that is distance t over time interval, we have 50 meters plus another 50 meters and another 30 meters. So the total is 130 meters, then divided by 12 seconds gives a speed of 10.83 meters per second. The answers show that the average speed is greater than the magnitude of the average velocity, since the distance traveled during this time interval is higher than the magnitude of displacement. Once again, congratulations for answering exercise number 2. We have learned earlier that the position of an object is a function of time. As time advances, the position may change depending on how a body moves. With this relationship, we can investigate motion graphically. Here we are going to learn two motional graphs, the position time graph and the velocity time graph. Let us begin with the position time graph. Position time graph, xt or yt graph, is a graph of body's position as a function of time. It is composed of two coordinates, vertical and horizontal coordinate. The vertical coordinate represents body's position while horizontal coordinate represents timeline. The figure below shows how the position of moving car relative to stop sign is being translated to the position time graph. The shape of the curve is determined on the actual positions of the car between time 0 second to 2 second. By just looking at the graph without seeing the car for as long as this graph represents its motion, we can determine its position at any point in time from 0 second to 2 seconds. At 0 second its position is 10 meters from the arbitrary origin. At 1 second it is around 16 meters. And at 2 seconds it is 20 meters. Position time graph is a very important tool in analyzing motion. One of its uses is that if we plot 2 points on the graph which corresponds to a given time interval, let's say between 0 seconds to 2 seconds, and then connect these 2 points with a straight line, we see that this line has a slope. From geometry, slope is computed by dividing the rise to the run of the line. We see that the rise is simply the displacement delta x, which is final position minus the initial position, 20 meters minus 10 meters, so the rise is positive 10 meters. The run is the time interval delta t, 2 seconds minus 0s, so it's run 2 seconds. So the slope is 5 meters per second, which is also the value of the average velocity. Therefore, we can say that the slope of the line between 2 points on the position time graph is equal to the average velocity of the object. Now let us give another example. Problem number 4. The figure below shows the position x of the car as a function of time t. Letter A. Sketch the position time graph of the car. Assume that the maximum and minimum positions are 50 meters and negative 50 meters, respectively. B. Referring to the graph, determine the average velocity of the car between time interval 2 seconds to 5 seconds, 5 seconds to 12 seconds, and 0 seconds to 10 seconds. So again, according to problem statement, we are going to draw a position time graph and the average velocity at each time interval listed below. To do this we need a graphing paper, then plot the position of car at each indicated time. At 0 second, 0 meter. At 2 seconds, 30 meters. At 5 seconds, 50 meters. Then the car started to move backwards. And at 7 seconds, 40 meters. At 10 seconds, the car has returned to origin. At 12 seconds, negative 30 meters. And lastly, at 15 seconds, negative 50 meters. Then connect the plotted point with a smooth curve. Although the curve is only an estimation, since we are limited with the information, it should look like this. Now for the average velocity, we just connect the points on each required time interval, then compute the slope of each line by dividing its rise to its run. So for 2 seconds to 5 seconds, so this is the line and the slope or the average velocity is 50 meters minus 30 meters, divided by 5 seconds minus 2 seconds. The average velocity between this time interval is positive 6.67 meters per second. For 5 seconds to 12 seconds, doing the same procedure. Create a line and get the slope, that is negative 30 meters minus 50 meters dividing 12 seconds minus 5 seconds will give an average velocity of negative 11.42 meters per second. Our slope is sloping downward, therefore we have negative average velocity at this time interval. From 0 seconds to 10 seconds. We see that this line is a horizontal line, so the slope is 0, and therefore the average velocity between this time interval is also 0. In the previous section, we have discussed the average velocity of a body at a given time interval. Remember that average velocity does not describe the velocity of a body at a given period of time. Referring to the position time graph shown, The average velocity of the body between time interval 0 seconds to 2 seconds is the slope of this line, so it is 10 meters. The rise divided by the run 2 seconds will give an average velocity of positive 5 meters per second. Now let us say, we want to know the velocity of the car at instant the time is 0 second. To answer this, we introduce another type of velocity called instantaneous velocity. It indicates what is happening at any point of time. Mathematically, instantaneous velocity v is the limit of the average velocity as the time interval becomes infinitesimally short, or as the time interval approaches zero. It is also the first derivative of the position with respect to time dx over dt. Now let us illustrate this. To determine the instantaneous velocity of the body at time 0 second using the position time graph, we bring the final point f closer to the initial point I. Take note the time at the initial point I is 0. As you can see, the run of the slope or the time interval is decreased. And as you continuously move the final point f closer and closer to point I, the time interval is getting smaller and smaller until such time that the final point I approaches the initial point I, hence the time interval approaches to 0. Surprisingly, the line seems to intersect at a single point on the graph and it is very small. Now we try to stretch this line. This line is called the tangent line at initial point I where the time is 0 second. And the slope of this tangent line represents the instantaneous velocity at time 0. If we try to compute the slope, so the rise is around 22.5 meters minus 10 meters equal 12.5 meters and the run is 1 minus 0 equals 1 second. Then dividing these, hence the instantaneous velocity, or simply, the velocity of the body at time 0 second is positive 12.5 meters per second. Now let us say that you are driving a car and you notice that the speedometer reads 25 miles per hour. Is the reading the velocity or speed of the car? Actually, the magnitude of the instantaneous velocity is what you read on a car's speedometer. And this magnitude of the instantaneous velocity is also the instantaneous speed of the body. In succeeding sections, when we use the term velocity we always mean instantaneous velocity. Let us solve this problem. Problem number 5. A particle moves along the x-axis. Its position varies with time according to the expression position x equals 2 times t squared minus 4t, where x is in meters and t is in seconds. The position time graph for this motion is shown in the figure. Because the position of the particle is given by a mathematical function, the motion of the particle is completely known. Notice that the particle moves in the negative x direction for the first second of motion, is momentarily at rest at the moment time t equals 1 second, and moves in the positive x direction at times t greater than 1 second. Letter A. Determine the displacement of the particle in the time intervals 0 to 1 second and 1 second to 3 second. Letter B. Calculate the average velocity during these two time intervals. Letter C. Find the instantaneous velocity and instantaneous speed of the particle at time 2.5 second. So here we have given position equation x equals 2t squared minus 4t. Required quantities are displacement delta x and average velocity from 0 second to 1 second and from 1 second to 3 second. Also, instantaneous velocity v and instantaneous speed s at 2.5 second. For delta x from 0 to 1 second, first thing we need to do is to determine the initial and final positions for specified time interval. If we refer the position time graph we see that, x sub I equals 0 and x sub f equal negative 2 meters. Another approach that you can do, in absence of graph or if you find difficulty in reading the exact value of the position, we can solve the positions using position equation by substituting the values of time t. So using the position equation if t equals 0 second, x sub I is equal to 0. If t is 1 second, using the position equation again, x sub f is negative 2 meters. These values agree with the values shown in the graph. So the displacement delta x from 0 to 1 second is -2 meters. We use similar approach for delta x from 1 second to 3 second. Referring to the graph, we get x sub I is -2 meters and x sub f 5 meters, so the displacement is 7 meters. Again, you can self-check the values of x sub I and x sub f using the position equation. For average velocity, we simply divide these displacements with the time intervals delta t. The average velocity for time interval 0 to 1 second is -2 meters per second. For time interval 1 to 3 seconds, the average velocity is positive 3.5 meters per second. Now, take a look carefully. Basically, you can also use calculus-based approach as alternative solution. We said earlier that the first derivative of the position equation x with respect to time t will give velocity equation. So we get the first derivative of the position equation as 4t minus 4, and this is called the velocity equation. This equation can be used to determine the instantaneous velocity at any time t. Now let us see if this thing works. Let's say between 0 to 1 second, we solve the instantaneous velocities using the generated velocity equation. At time 0 second, the initial velocity v sub I is -4 meters per second. At time 1 second, the final velocity v sub f is 0. Lastly, we solve the average velocity by simply averaging these two velocities. So we have -2 meters per second. This result conforms with our answer using delta x divided by delta t. Find it challenging? Try this method for time interval 1 to 3 second. For instantaneous velocity v and instantaneous speed at 2.5 second, there are two ways in doing this, using position time graph and using velocity equation. From the position time graph, draw a tangent line with the curve at time 2.5 second. The slope of this tangent gives the instantaneous velocity at this time. Just be more cautious in estimating the tangent line to the values of rise and run more accurate. I choose this as rise. I think this is around 5 meters minus -1 meter. And the run is 3 second minus 2 second. Dividing rise by run, so the instantaneous velocity at 2.5 second is 6 meters per second. From here, the instantaneous speed s is simply 6 meters per second. It is just the magnitude of the instantaneous velocity. If you find this graphical approach tedious, don't worry. Now I will show you an easier approach. Again, we can use the velocity equation we have constructed earlier from the first derivative of position equation, that is v equals 4 tons minus 4. We just solve for the value of v when the value of time t is 2.5 seconds. So we get also the value 6 meters per second. Hello, we meet again. How are you? I hope you're fine. Have you answered exercise number 3? If yes, then congratulations. If no, then study again and try to focus more or talk to your teacher. In this lesson, I will introduce another kinematic quantity called acceleration. Maybe you experience change in speed or velocity, especially when you are riding a car, either when the car is speeding up or slowing down as time goes by. We may say that the car is either accelerating or decelerating. In physics, this change in velocity as a function of time is called acceleration. In this section, same as with velocity and speed, we will explore average acceleration and instantaneous acceleration. Average acceleration, denoted by a sub a v, is the time rate of change of the velocity, or instantaneous velocity. Mathematically is expressed as change in velocity delta v over time interval delta t. That is also final velocity v sub f minus initial velocity v sub I divided by the final time t sub f minus initial time t sub I. The SI unit of acceleration is meters per second squared. It can be also expressed, in other unit systems, as centimeter per second squared or feet per second squared. To illustrate this, The car in the figure moves initially at a velocity of 10 meters per second, accelerates to 25 meters per second in a time interval delta t of 3 seconds. The change in velocity delta v at this time interval is 15 meters per second, and dividing this by delta t 3 seconds, therefore, the car accelerates at positive 5 meters per second squared. It means that this car is speeding up by 5 meters per second in every 1 second. If the car continues at this acceleration, then after succeeding 1 second of movement, its velocity becomes 30 meters per second, 35 meters per second and 40 meters per second, and so on. Acceleration is a vector quantity. In one-dimensional motion, positive or negative is enough to denote its direction. The sign of acceleration and the initial velocity will dictate whether the object is accelerating or decelerating. Consider the following points. When the initial velocity and acceleration are in the same direction, either both positive or both negative, then the object is accelerating. But when the object's initial velocity and acceleration are in the opposite directions or different signs, the object is decelerating. Beware! It is a misconception that a negative value of acceleration necessarily means the object is slowing down. If the acceleration and initial velocity are both negative, then the object is speeding up and not slowing down. Another thing to consider is that the initial velocity is 0 when the body is initially at rest, while the final velocity is 0 when the body stops moving. Another useful motional graph that we are going to consider is the velocity time graph. It is a graph of body's velocity as a function of time. Using this graph, we can easily determine the velocity of a body at specific point in time. For instance, in figure, we can estimate that at 2 seconds, the car is moving at a velocity of around 16 meters per second. Now, if we connect 2 points I and point F of the graph with a diagonal line, we see that the rise is the change in velocity and its run is time interval delta t, and dividing rise by run gives the slope of this line, which represents the average acceleration. Here we have a rise of 15 meters per second and a run of 3 seconds, therefore the average acceleration between time interval 0 to 3 seconds is 5 meters per second squared. The type of acceleration that we have discussed in previous section is only the average acceleration at certain time interval. We do not know yet the acceleration of at any specific time. Now we are ready to explore another type of acceleration called instantaneous acceleration. Instantaneous acceleration is the limit of the average acceleration as the time interval goes to 0. It is also the first derivative of the velocity with respect to time. Same thing as we did before in instantaneous velocity, using the velocity time graph, we can determine instantaneous acceleration at any time by constructing a line tangent to the curve at a specific time. The slope of this tangent line represents the instantaneous acceleration at that time. In next section, we shall see a constant instantaneous acceleration, which is represented by a diagonal line on the velocity time graph rather than a curved line. When the instantaneous accelerations are always the same, then object is undergoing a motion called uniformly accelerated motion. Okay, we give another sample problem. Problem number 6. An astronaut has left an orbiting space shuttle to test a new maneuvering unit. As she moves along a straight line, her partner on board the shuttle measures her velocity every 2 seconds, starting at time 1 second, as follows. So here's the table. Letter A, draw the velocity time graph of the astronaut. Letter B, find the average acceleration, for each of the following time intervals, 1 second to 3 seconds, 5 second to 7 second, 9 second to 11 second, and 13 second to 15 second. Describe also whether the astronaut is accelerating or decelerating at each time interval. Letter C, using the constructed graph estimate, the instantaneous acceleration at time 14 second. Again, we are asked to construct the velocity time graph, the average acceleration at specified time intervals and instantaneous acceleration at 14 seconds. We need again a graphing paper to construct the velocity time graph, then plot the velocity of the astronaut at each indicated time. At 1 second, 0.8 meter per second. At 3 second, 1.2 meter per second. At 5 second, 1.6 meter per second. At 7 second, 1.2 meter per second. At 9 second, negative 0.4 meter per second. Negative velocity indicates that at 9 second the astronaut is now moving in the opposite direction. At 11 second, negative 1 meter per second. At 13 second, negative 1.6 meter per second. At 15 second, negative 0.8 meter per second. Then connect the plotted points with a smooth curve. Although the curve is only an estimation, since we are limited with the information, it should look like this. Now we're ready for average acceleration. Average acceleration is equal to change in velocity divided by the time interval. For time interval 1 second to 3 second, the change in velocity is 1.2 minus 0.8 meters per second divided by 3 minus 1 second, will give an acceleration of positive 0.2 meter per second squared. Since the initial velocity and acceleration are both positive, therefore the astronaut is accelerating during this time interval. From 5 second to 7 second, we have a change in velocity of 1.2 minus 1.6 meter per second divided by 2 seconds time interval. This gives an average acceleration of negative 0.2 meter per second squared. The astronaut is decelerating since the initial velocity and acceleration have different directions or signs. For 9 to 11 seconds, the average acceleration is negative 1 minus negative 0.4 divided by 2 second equals negative 0.3 meter per second squared. We see that the initial velocity and acceleration are both negatives, therefore the astronaut speeds up or accelerating at this time interval. For 13 to 15 seconds, dividing the change in velocity of negative 0.8 minus negative 1.6 meter per second by 2 second will give an average acceleration of 0.4 meter per second squared. The initial velocity is a negative while the acceleration is a positive, therefore the astronaut decelerates in this time interval. I hope you got everything understood. Lastly, for instantaneous acceleration at time 14 second, from the velocity time graph we have constructed a while ago, we draw a line tangent to the curve at 14 second. Then we determine the slope of this line. Careful observation show that the rise is around negative 1 minus negative 1.8 meter per second and the run is 15 second minus 13 second. Finally, we get the acceleration as rise over run. So the acceleration of the astronaut at time 14 second is 0.4 meter per second squared. So that's it. Thank you for listening. You should take a break if you feel exhausted. See you later. At this point, I believe that you have already acquired basic knowledge on motion graphs such as position time and velocity time graphs. The next thing you should possess is to have a clear understanding on how we interpret these graphs. We will take a look on the shape of the lines that can be generated at different situations. Number 1, when the body is at rest, or no relative motion. Number 2, when the body is moving at constant velocity. Number 3, when the body is accelerating at constant rate, and Number 4, when the body is decelerating at constant rate. So let's begin. For no motion or at rest. A body is at rest when its position does not change relative to some frame of reference. Imagine a person standing still and there is a tree which acts as the reference origin. If the person is standing beneath the tree, we can say its position relative to the tree is 0. As long as he is not moving, his position remains 0 as time goes by. So we see a horizontal line on the timeline of position time graph. When the person is standing still 10 meters right of the tree, this line will be a horizontal line at 10 meters, which is above the timeline. If the person is standing on the opposite side of the tree, then the horizontal line will be below the timeline. at x equals -10 meters. In case of velocity time graph, since the person is standing still, therefore its velocity is 0 at any time. We see a horizontal line on the timeline regardless on the position of person relative to the tree. For uniform motion or constant velocity, a body is moving uniformly or at constant velocity when the distances it moves are equal for equal time intervals. Let's say a car is traveling 5 meters every 1 second. At 0 second, the position is 0. 1 second later the car is 5 meters away from position 0. 2 seconds later, 10 meters. And 3 seconds later, 15 meters. Therefore, its velocity is constant 5 meters per second. If a body is traveling towards positive x-axis, the line is sloping upward while a downward slope means that the body is moving towards negative x-axis. For velocity time graph, a horizontal line above or below the timeline represent this type of motion. Since this car is moving along positive x-axis at constant 5 meters per second, this will give a horizontal line above the timeline. If it is moving along negative x-axis, then the horizontal line is below the timeline. Now for accelerating at constant rate. A body is accelerating when the distances it moves are increasing during equal time intervals. The position time graph shows a parabolic curve with increasing slope. Since this car is moving toward positive x-axis, so the curve is drawn above the timeline. But if it is moving towards negative x-axis, the curve is drawn below. For the velocity time graph, let's say that this car increasing its velocity by 5 meters per second for every second, so if it is moving towards positive x-axis, therefore we can construct a diagonal line sloping upward. If it is moving towards negative x-axis, the line is sloping downward. Lastly, for decelerating at constant rate. A body is decelerating when the distances it moves are decreasing during equal time intervals. The position time graph shows a parabolic curve with decreasing slope. The curve is drawn above the timeline if the object is moving towards positive x-axis. And the curve is below the timeline if it is moving towards negative x-axis. The velocity time graph shows a diagonal line which is sloping towards the timeline. Since this car is initially moving fast and gets slower and slower towards positive x-axis, so we can construct a diagonal line which seems to be closer and closer to the timeline. If the body is towards negative x-axis, the velocity becomes less and less negative. Let us answer this problem number 7. The position of an object moving along x-axis varies with time as shown in the figure. Letter A. Determine the type of motion in each time interval, indicated by letters, and tell whether the object is moving towards positive x-axis or negative x-axis. Letter B. In what point or points the instantaneous velocity is 0. Letter C. Sketch the velocity versus time graph for the object. So again, we are asked to determine the type of motion in each time interval, point or points where the velocity is 0, and a sketch of velocity time graph. Referring to the given position time graph and applying what we have learned from the previous section, we tabulate our answers for clarity. From points A to B, the line is a curve with increasing tangent slope, therefore, the object is accelerating at constant rate and it is moving towards positive x-axis. From B to C, the line is a diagonal sloping upward, so the object has uniform motion or moving at constant velocity and it is still moving towards positive x-axis. At point C, the object begins to decelerate to point D while traveling toward positive x-axis. And momentarily at point D, the object has stopped moving. Then from point D, it begins to accelerate backwards or towards negative x-axis, until point E. From point E, the object decelerates while traveling towards negative x-axis, until it comes to rest at point F. Lastly, at points F to G, Since the line is a horizontal, the object maintains at rest. For letter B, at what point the velocity of the object 0? So we try to observe a point on the position time graph wherein the slope of the tangent line is 0, hence 0 velocity. We can observe 4 points with that meet the criterion, at points A, D, F and G. At these points the object is at rest or 0 velocity. For the velocity time graph, from point A to point B, the type of motion is accelerating, so we have a diagonal line sloping upward. From points B to C, constant velocity, so we have a horizontal line. At point C, the object started to decelerate until it stopped at point D. So point D should hit the timeline. Then the object accelerates backward, so the velocity at point E is a negative value. Finally, it decelerates to point F to a velocity of 0 and at point G as well. Take note that this is only a sketch and we cannot determine the value of velocity at each point since we do not have enough information on the values of position from the position time graph. Later, we will see another surprising fact, that the area under the velocity time graph represents the displacement and the total distance traveled by the object. Hello, everyone. At this point, it is expected that you have mastered the concept of kinematic quantities such as position, time, displacement, distance, speed, velocity and acceleration. In this lesson, we will learn an important type of motion in which the velocity of a body is changing at constant rate. This motion is called uniformly accelerated motion. Uniformly accelerated motion is a type of variable motion in which the velocity of a body changes at the same rate throughout the motion. The car in the figure shows this type of motion. At time 0 second, the car is initially at rest, accelerates to 5 meters per second 1 second later, 10 meters per second in 2 seconds and 15 meters per second in 3 seconds. We see that the velocity of the car is increasing at a constant rate of 5 meters per second in each second, therefore its acceleration is 5 meters per second squared. Furthermore, uniform acceleration means that the average acceleration between any time intervals is constant. This average acceleration is also the instantaneous acceleration at any time. To begin with the anatomy of equations for uniformly accelerated motion, let us consider again a car in which, initially at time t sub I which is 0, it has an initial position x sub I from the stop sign as origin and moving towards positive x-axis at a velocity of v sub I. Then the car speeds up with constant acceleration a. At later time t sub f, its position is at x sub f with a final velocity of v sub f. Now this is where the story begins. Let us wrap up the 3 basic equations first. We recall that the average velocity is equal to the change in position delta x over time interval delta t. Then the average acceleration is equal to the change in velocity delta v divided by the delta t. We can also express average velocity as half of the sum of the initial and final velocities, which is applicable only for uniformly accelerated motion. We transform these equations by allowing t sub I equals 0 and t sub f be the time interval t, which means the time t is any later time from 0 second. We also change the average acceleration to instantaneous since the acceleration is constant. So this is the transformed basic equations and we mark them as equations A, B and C, respectively. Now from these 3 basic equations, we will derive 5 specific equations to be used in dealing with motion with constant acceleration. From equation B, final velocity v sub f can be expressed as the initial velocity v sub I plus the product of acceleration a and time t. So this is the first specific equation. Now for the second equation, we combine equations A and C. So the displacement x sub f minus x sub I is equal to half of the sum of the initial velocity v sub I and final velocity v sub f multiplied by time t. So this is the second equation. This equation is useful especially when solving final position x sub f with known final velocity at any later time even if we do not know the value of acceleration. For the third equation, with known value of acceleration and without knowing the value of final velocity, we combine equations 1 and 2, so the final position x sub f can be expressed as the sum of the initial position, the product of initial velocity and time and half of the product of acceleration and square of time. Likewise, in terms of final velocity and without requiring the value of initial velocity, so from equation 1, we solve v sub I as final velocity minus acceleration multiplied by time. Then combining to equation 2 gives another expression for final position x sub f as x sub I plus v sub f minus 1/2 at squared. And this is the fourth equation. Lastly, for the fifth equation, if we solve for time t from equation 1 and substituting to equation 2, we can have derived the expression v sub f squared equals v sub I squared plus 2a multiplied by x sub f minus x sub I. This equation is useful especially when dealing with problems wherein time t is not given. So remember these 5 equations. We will use these equations frequently so as much as possible memorize them. Of course, before using these equations in a particular problem, the first thing you need to do is to analyze carefully the problem, properly identify given information and quantities to be solved, then select the most appropriate and simplest formula that will give the shortest solution as possible. It is also suggested to consider the following. Set the initial velocity to 0 if the body is initially at rest. Set the final velocity to 0 if the body stops moving. Acceleration is constant at any time t but the final velocity varies with time. Let the initial position x sub I be 0 unless otherwise specified in the problem. If the velocity is constant, that is v sub I is equal to v sub f, you can set acceleration to 0. Then the 5 equations are reduced to displacement equal the product of constant velocity v and time t. Now, to have a different view on this, let us investigate how these equations mean to our motional graphs. Consider a velocity time graph of a body, moving initially at a velocity v sub I then accelerates at a constant rate a which is represented by the slope of this line. At later time the velocity has changed by this height at. It is clear seen from this graph that if we add v sub I and at the result will be the final velocity v sub f which agrees with equation 1. In addition, the area under this line represent the displacement delta x of the body at later time t. Now from geometry we see a trapezoidal area which can be divided into a rectangle and a right triangle. We knew from geometry that the area of a rectangle is base multiplied by its height, so the area of this rectangle is v sub I multiplied by later time t. While for this triangle, in which the area is 1/2 base time height, has an area of 1/2 a times t squared. Adding these two areas will be the body's displacement delta x. Surprisingly this agrees with equation 3. Now let us use these equations in solving problems. Problem number 8. A jet lands on an aircraft carrier at a speed of 140 miles per hour, approximately 63 meters per second. Letter A. What is its acceleration, assumed constant, if it stops in 2 seconds due to an arresting cable that snags the jet and brings it to a stop? Letter B. If the jet touches down at position x sub I equals 0, what is its final position? Letter C. If the overall length of the aircraft carrier 100 meters, do you think the jet landed safely? So establishing given information, here we have the initial velocity of the jet which is 63 meters per second. At time 2 seconds, the jet has stopped, so set final velocity to 0. X sub I is also 0 according to problem statement. And the length of the aircraft is 100 meters. So the problem requires to solve for the acceleration of the jet, its final position, and we are going to verify if the jet landed safely. Before we solve this, make sure you have a copy, may be on a piece of paper, the 5 equations we derived earlier. This will serve as quick reference. So for letter A, based on the given information, to solve for acceleration, we can use equation 1, that is v sub f equals v sub I plus a times t. Then we will do some algebraic transformation so we can solve for the acceleration. If you do that, acceleration will be the quantity of v sub f minus v sub I divided by the time interval t. Substituting values, 0 minus 63 divided by 2 will give an acceleration of negative 31.5 meters per second squared. Letter B, we select equation 2 in solving the final position x sub f. From this equation, we can eliminate x sub I and v sub f since their values are zeros. Always remember we can eliminate immediately from the equation those with zero values. This is to make our equation simpler. Then substituting the given values. 1/2 of 63 times 2 will give jet's final position of 63 meters. By the way, you can also use equation 3 to solve for x sub f, but make sure you have answered acceleration in part A correctly. Letter C, to verify if the jet landed safely, we just compare the final position of the jet and the length of the aircraft carrier. Since the final position of jet, that is 63 meters, is less than 100 meter length of aircraft carrier, therefore the jet landed safely. Good thing there is a resting cable that serve as added braking system. Now let us conclude what we have discussed about uniformly accelerated motion, by considering this sample problem. Problem number 9. The performance of new model car is being tested as it moves straight along a horizontal ground. The car, initially at rest, accelerates to 10 meters per second for 3 seconds. It moves at constant velocity for 5 seconds, and accelerates at a constant rate of 6 meters per second squared for 6 seconds. It moves again at a constant speed for 1 minute or 60 seconds. Then it comes to rest for 10 seconds. Letter A, find the total distance traveled for the entire trip. Letter B, what is the average speed for the whole journey? Letter C, what is the maximum velocity attained by the car? Letter D, draw the velocity time graph for the whole journey. And verify your answer in part A using this graph. This problem is quite long because we are required to solve for the total distance traveled, the average speed, the maximum velocity, and to construct a velocity time graph. For letter A, the total distance traveled. The figure shows the type motion happening in each time interval. We also indicate the known values of velocities, time and acceleration. Since the car is moving along a straight line, therefore the total distance traveled d is the same as the magnitude of the car's displacement delta x. By knowing the initial and final velocities at each type of motion, we solve for the distance traveled delta x sub a, delta x sub c and delta x sub b, using the equation delta x is equal to 1/2 of the quantity initial velocity plus final velocity multiplied by time t. For delta x sub b and delta x sub d, we use delta x equals vt, since they involved constant velocity motion. For delta x sub a, we see that the initial and final velocities are 0 and 10 meters per second, respectively. The distance traveled for the first 3 seconds will be 1/2 of 10 multiplied by 3. So delta x sub a is 15 meters. For delta x sub b, this involved constant velocity. Delta x sub b is vt, that is 10 meters per second time 5 seconds. So the second distance is 50 meters. Let's keep up. For delta x sub c, we solve first for the final velocity v using the equation, v sub f equals v sub I plus a time t. Substitute the values, 10 plus 6 times 6. So the final velocity will be 46 meters per second. Then using the displacement formula and substituting the values, 1/2 of the quantities 10 plus 46 times 6, will give a distance or displacement x sub c of 168 meters. Can you still follow? You may pause a while or you may rewind my explanation. Now for delta x sub d. It involves again constant velocity motion. So it is also v times t, 46 times 60. Therefore, delta xt is 2760 meters. Lastly, for delta x sub b, we have already initial and final velocities, 46 and 0, so no problem at all. Delta x is equal to 1/2 of 46 times 10. So delta x sub b is 230 meters. After solving the individual distances traveled for each type of motion, now we're ready to solve for the total distance by simply adding all of these distances from delta x sub a to delta x sub b. Therefore, the total distance traveled by the car is 3,223 meters. For average speed, we simply use the formula speed s equals distance d over time interval. We have already solved the distance to be 3,223 meters. For the total time interval delta t, we just had all of these indicated periods of time, so it is 84 seconds. Therefore, the car's average speed is 3,223 meters divided by 84, 38.4 meters per second. For maximum velocity v sub max, by observing our solution in part A, we see a maximum velocity of 46 meters per second. Although the car has attained a maximum velocity of 46 meters per second, its average speed is only 38.4 meters per second. Take note that maximum velocity is instantaneous velocity in nature. Now, for the last item on the required list, the velocity time graph. The first thing you need to do is to check the value of velocity at each indicate time. So at 0 second, the velocity is 0. 3 seconds later, the velocity becomes 10 meters per second. Plus 5 seconds later, so 8 seconds later, the velocity is still 10 meters per second. Plus 6 seconds later, so 14 seconds later, its velocity is 46 meters per second. Then at additional time of 60 seconds, therefore 74 seconds later, the velocity is still constant to 46 meters per second. Lastly, a 10-second additional time, or 84 seconds late, the car has stopped so the velocity is 0. After checking these velocities, I guess we're all set to construct the velocity time graph. I conveniently use 10-second increment for the timeline as well as for the velocity line. Now we plot the points, use the values of velocity and time. First point will be 0 and 0. Then 3 and 10. 8 and 10. 14 and 46. 74 to 46 and 84 to 0. Then we connect these points using straight line. And this is how the velocity time graph for the car looks like. Now using the velocity time graph, we can determine the displacement or total distance traveled by the car. The area under the graph represent the displacement, or total distance, traveled by the car. We see that each displacement has a shape, either a triangle, rectangle or trapezoid, and applying the formula of geometric area of these shapes will give a total area of 3,223 meters. This triangle area is actually the delta x sub a, which is the 1/2 3 times 10. This rectangle area is delta x sub b, that is 5 times 10 from this expression. This trapezoidal shape represents delta x sub c, which is the 1/2 times 6 multiplied by the sum of 10 and 46. This large rectangle is the delta x sub d, which is, from the equation, the 60 times 46. And lastly, delta x sub e is represented by this triangle, and the area is 1/2 of 10 times 46. The total area of this shape represents the car's displacement for the 84-second journey. As expected, this value is the same as our answer in part A. In previous section, we have solved several problems involving uniformly accelerated motion along x-axis. In this section we will be discussing free fall, that also employs motion with constant acceleration, but this time along the y-axis or vertical line. When we say free fall, it is a type of motion with constant acceleration due to the influence of the Earth's gravitational attraction. This gravitational attraction, or gravity, is exerted on all bodies and is nearly pointing to the Earth's center. Some examples of free fall are throwing a ball straight up in the air, a diver jump from a diving board, and a ball drops freely from your hand. In the 4th century BC, Aristotle, a Greek philosopher, thought that a given body falls faster than lighter ones. This was accepted as fact until the Italian physicist and astronomer Galileo Galilei conducted his experiment, in 16th century, with two objects of the same material but different weights dropped from the Leaning Tower of Pisa. His experiment concluded that all bodies initially having the same height would fall to the Earth's surface at the same time. Although the result of Galileo's experiment on falling bodies is accepted, influences besides gravitation are unavoidable. Air resistance in the Earth's atmosphere, distance of the falling object from the Earth, and the Earth's rotation are the three major things that affect falling body. Therefore, he pointed three assumptions to make his experiment valid. Number 1, air resistance is neglected. Consider a glass tube filled with air. And there are two objects, a heavy metal and a light feather. With the presence of greater air drag on the feather as compared to the metal, we see that the metal falls faster than the feather. But once air is evacuated from the glass tube, they would fall at the same time since the effect of air drag is eliminated. Number 2, the effect of Earth's rotation can be neglected. Imagine this is the Earth's center, which has a distance radius from the surface. At a location near the equation, the Earth's surface is moving at a linear speed of around 460 meters per second. If we released a ball at a certain height h, its point of impact will be affected somehow by the Earth's rotation. Here, we will neglect that effect. Lastly, number 3. The height of fall is very less than the Earth's radius since the gravitational attraction decreases with elevation. We will take a look in more details on the effects of variation of gravity later. Now let us consider the kinematics of a free fall. First thing to discuss is the acceleration due to gravity, which is denoted by small letter g. In small region, near the Earth's surface, the acceleration due to gravity is uniform in both direction and magnitude and is equal to 9.8 meters per second squared in SI unit system, and 32.2 feet per second squared for English system. As you can see in the figure, we neglect the variation of the magnitude of gravitational acceleration for a small region near the Earth's surface. And this is what we are going to apply. We will follow the third assumption of Galileo. However, if we take a look on larger and farther regions, the magnitude decreases with increasing elevation. So at farther regions the gravitational acceleration is less than 9.8 meters per second squared. A free fall may be in two scenarios, falling and rising. The magnitude of the velocity of a falling body is increasing by 9.8 meters per second for every second. It means that when you release an object from rest, the magnitude of its velocity becomes 9.8 meters per second 1 second later. It becomes 19.6 meters per second 2 seconds later, 29.4 meters per second 3 seconds later, and so on. In terms of the magnitude of vertical displacement, we see that it is increasing in each second. With these changes in velocities and displacements, we assume that the gravitational remains constant. Now let us investigate how the motional graphs look like for a falling body. For the position time graph, since a falling body moves downward and if we take the origin at higher location, the positions as function time are negative values. For the velocity time graph, the velocities are negative values since a falling body moves along negative y-axis. We see that the magnitude of velocity is increasing as it falls. In other words, a falling body accelerates. On the other hand, a rising body is decelerating at the constant rate of 9.8 meters per second for every second. When we throw an object vertically upward with an initial velocity of 29.4 meters per second, because of the opposite direction of gravitational acceleration, its velocity becomes 19.6 meters per second 1 second later. 2 seconds later its speed becomes 9.8 meters per second. And 3 seconds later, the object momentarily stopped, hence the velocity is zero when it reaches the maximum height of flight. Also we see that the magnitude of its vertical displacement is decreasing in each second. Again, although both the positions and velocities are changing, we assume that the acceleration due to gravity remains constant. We can also say that a rising body is decelerating as it rises. For position time graph, since a rising body moves upward and if we take the origin lower location, the positions as, of course as function of time, are positive values. For the velocity time graph, the velocities are positive values since during its course all the way up, it moves toward the positive y-axis. We see in this graph that the magnitude of velocity of a body is decreasing as it rises. Now you're going to learn the related equations for free fall. We consider first a falling body. At an initial time 0, the body is at initial position y sub I from assigned origin with an initial velocity of v sub I. We knew already that a falling body accelerates due to gravity, so at later time t, both its position, the final position y sub f and the velocity v sub f have changed. On the other hand, for a rising body, the body is at initial position y sub I from the origin at time 0. At this point it has an initial velocity of v sub I. As it moves against the gravity and the position has changed to y sub f, the magnitude of its velocity is decreased to v sub f. Now, it's time for the equations. Since we already assumed that a free fall has constant acceleration in small region near the Earth's surface, we can use these 5 equations for uniformly accelerated motion. You should not forget these equations. These equations are very useful in many aspects of physics, especially when we are dealing with Newton's second law of motion in next unit. So how we are going to use these equations for motion of free fall? It is very simple. Since a free fall follows a vertical path as it moves, we only change the position x to y. And the acceleration a will be changed to negative of g. We put negative sign besides g because g is always downward. Doing these things, so equation 1 will become final velocity v sub f is equal to the initial velocity v sub I minus gravitational acceleration g multiplied by time t. Second equation will be final position y sub f minus y sub I, so this is also the displacement delta y, is equal to the half of the sum of the initial and final velocities multiplied by time t. For third equation, y sub f equals y sub I plus v sub I t minus 1/2 gt squared. Fourth equation is y sub f equals y sub I plus v sub f t plus 1/2 gt squared. And for the fifth equation, v sub f squared equals v sub I squared minus 2g multiplied by the quantity y sub f minus y sub I. These are the 5 kinematic equations for free fall. Take note that these equations are applicable for both scenarios, falling and rising. You do not need to make some adjustment on the signs of variables, especially the sign of gravitational acceleration in the equation. The equations always fit for both falling body and rising body. Be careful also on the signs of the velocities. As the body moves upward, its velocity is positive. But once the body moves downward, its velocity becomes negative. Do not forget and always follow this very important sign convention for velocity. Aside from understanding these free fall equations, keep in mind the following important points. The initial velocity v sub I is 0 if the body is initially at rest and drops freely. The final velocity v sub f is 0 if the body has reached the maximum height of flight during rising. When a body is thrown vertically upward, It will reach the maximum height at a time, let's say 2 seconds, equal to the time it took from the maximum height to its original position, so the time of fall is also 2 seconds. With this, we can say that the time of flight is equal to the sum of time to rise and time to fall. Do you have any questions in mind? You can clear things up by communicating with your teacher or have online collaboration with your classmates. Okay, now let's answer this free fall problem. Problem number 10. You throw a ball vertically upward from the roof of a tall building. The ball leaves your hand at a point even with the roof railing. With an upward speed of 15 meters per second, the ball is in free fall. On its way back down, it just misses the railing. At the location of the building, g equals 9.8 meters per second squared. Find. Letter A, the position and velocity of the ball 1 second and 4 seconds after leaving your hand. Letter B, the velocity when the ball is 5 meters above the railing. Letter C, the maximum height reached and the time at which it is reached. We first established given information. The initial velocity is positive 15 meters per second. This is positive because, according to problem statement, the ball is thrown upward. It will be negative if the ball is thrown downward. Be careful on this, or else our solution will be messed up. G is 9.8 meters per second squared. We set initial position y sub I to 0, since we choose the thrower's hand as the origin. And we have two indicated time 2 seconds and 4 seconds. Required quantities are the final position and final velocity at 1 second and 4 seconds. Final velocity when the position of the ball is 5 meters above the railing. Maximum height and the time it reaches this position. To begin our solution, we put the ball on y-axis to visualize its position as it moves. So we have given the initial velocity positive 15 meters per second. We have set the initial position to 0 at time 0. Letter A, for the final position and final velocity at time 1 second and 4 seconds after throwing the ball. We use equations 1 and 3 for v sub f and y sub f, respectively. V sub f equals v sub I minus gt. And y sub f equals y sub I plus v sub it minus 1/2 gt squared. So at 1 second, applying equation 3 then substituting the given information, 15 times 1 minus 1/2 of 9.8 times 1 squared. The final position is positive 10.1 meters. Positive value means that the ball is located above the railing 1 second after throwing the ball. For final velocity, from equation 1, then substituting the values 15 minus 9.8 times 1, will give a final velocity of positive 5.2 meters per second. Positive velocity indicates that at time 1 second, the ball is still moving upward. At 4 second, we will do the same procedure while changing the time to 4 seconds. So the position of the ball 4 seconds later is negative 18.4 meters. Negative value means that the ball is located below the railing 4 seconds after throwing the ball. For final velocity, using again equation 1, its value is negative 24.2 meters per second. We see a negative velocity since it indicates that at time 4 seconds the ball is already falling. Let's continue to letter B. We calculate the final velocity of the ball when the ball reaches 5 meters above the railing or thrower's hand. Since we do not have available information on the time when the ball reaches this 5 meters, the appropriate equation to be used is equation 5, that is v sub f squared equals v sub I squared minus 2g times the quantity y sub f minus y sub I. Remember, this is the only free fall equation that do not require time. Then, we take the square root both sides of the equation. Substituting and pressing on the calculator the values, will give a final velocity of positive and negative 11.3 meters per second. So what this positive and negative signs mean? Try to observe that the ball reaches a position of 5 meters above the railing of the building twice. First is that when the ball is still rising, so the velocity here is a positive. Second is when the ball started to fall from maximum height and eventually it will reach again this 5-meter position with a negative velocity. For these reasons, we take two answers, positive and negative 11.3 meters per second. Lastly, letter C, for maximum height and the time at this point. Maximum height is a special term for final position y sub f when the final velocity is 0. We do not know yet the time, so we use again equation 5 for this. But we need to transform the equation because we want to know y sub f. So we will do some algebraic manipulation. Here we transposed v sub I squared to the other side of the equation. Then we can cancel out y sub I, since it is 0. Then dividing both sides by negative of 2g. So the transformed equation y sub f is equal to v sub f squared minus v sub I squared all over negative of 2g. Substituting values will give a maximum height y sub f of 11.5 meters. Take note, this is the maximum position of the ball. It will never reach any position above this. Then for the time, we simply use equation 1. Again we manipulate the equation to solve for time. We transposed v sub I to the other side and dividing both sides by negative g. So time t is equal to the change in velocity v sub f minus v sub I divided by negative of g. Substitute the values, will give a value of 1.53 seconds. It means that right after 1.53 seconds, the ball begins to move downward. Congratulations for answering exercise number 6. Great job! Don't forget to submit your output to your teacher. We're almost done in the study of kinematics. The two remaining lessons deal with motion in 2 dimensions, projectile motion and uniform circular motion. Now let us begin with projectile motion. Projectile is a body that is given an initial velocity and then follows a path determined entirely by the effects of gravitational acceleration and air resistance. It is a combination of horizontal and vertical motions. In our discussion, we will consider the following assumptions. The projectile moves vertically with constant acceleration due to gravity, that is 9.8 meters per second squared. The projectile moves horizontally at constant velocity when the effects of air resistance is negligible. With these two assumptions, basically a projectile is a 2-dimensional free fall which has a trajectory of parabola. And when we say trajectory, it is a path followed by a projectile. Depending on the direction of the initial velocity theta sub I, a projectile comes into 2 types. Type 1 projectile has an initial angle within the range of 0 to 90 degrees, or simply an acute angle. While a Type 2 projectile is launched horizontally, that is at 0 degree. The kinematic equations for projectile motion seems tedious, but in fact we will use old equations we have encountered before reaching this topic. Now listen very carefully. Since projectile motion is a 2-dimensional type of motion, it is convenient to analyze separately its kinematic quantities in terms of horizontal and vertical components. Imagine this as our projectile, let's say a ball. Considering it is a Type 1 projectile, it is given with initial velocity v sub I at an initial angle of theta sub I. So this is the trajectory, a parabola. We mentioned a while ago that horizontally a projectile moves horizontally at constant velocity and it follows free fall motion on vertical axis. In analyzing any type of projectile, the initial velocity should be resolved into x and y components using the initial angle. To do this, we will use sine and cosine functions. The x component of the initial velocity is v sub I cosine of theta sub I, while the y component is v sub I sine of theta sub I. For Type 2 projectile, the x component of the initial velocity is also the initial velocity itself since the initial angle of flight is 0. And the y component of the initial velocity is automatically 0. The position of a projectile, as a function of time t, is described by its x and y coordinates x sub f and y sub f, respectively. The initial velocity should be resolved into components and using the initial angle of flight. This is usually the preliminary step in order to solve other quantities such as the position and the final velocity of a projectile at any later time. Keep in mind that a projectile moves horizontally at constant velocity, hence the equation average velocity equal displacement delta x divided by the time interval delta t. So the horizontal position of a projectile x sub f is equal to the product of the x component of the initial velocity and time interval t. For a vertical position y sub f, we can utilize free fall equations. So y sub f is equal to v sub iy multiplied by time t minus 1/2 gt squared. Or it is 1/2 of the sum of the y components of the initial and final velocities multiplied by time. Be careful not to use directly the velocities vi and vf. What we need here are the y components of velocities. As the projectile moves, its velocity is changing as well as the angle of flight. So to determine this final velocity v sub f, we need to solve for its x and y components first. V sub fx is also equal to v sub ix, knowing that a projectile moves horizontally at constant speed. For the y component of the final velocity v sub fy, we use again free fall equations. At maximum height, same as with free fall, v sub fy is 0 for type 1 projectile. At this location, momentarily, its velocity is horizontally equal to the x component of the initial or final velocity. Afterwards, it begins to fall following the other half of trajectory as it returns to its initial elevation. Other formulas will be the magnitude and direction of the initial and final velocities. There is no problem here after knowing the x and y components of the velocities. We simply use Pythagorean theorem for the magnitude and the inverse tangent function of a right triangle. For type 1 projectile, we have derived equations for its horizontal range r and maximum height h. Note these are exclusive for type 1 projectile only. Range r is expressed as the square of the initial velocity multiplied by the sine of the twice of the initial angle all over g. While the maximum height h is equal to the square of the y component of the initial velocity over 2g. Lastly, we investigate here the ranges of a projectile launched with the same speed but at different angles. As you can see, a projectile that was launched at 45 degrees has the maximum range. We also observed that ranges are equal for complementary angles. For instance, the range of 15 degrees is the same as its complementary angle 75 degrees. However, their heights are different. Now let's have a final look on the kinematic equation for projectile motion. You don't have to memorize all of these equations, although it is an advantage. If you got a chance to understand the basics of uniform motion and free fall motion, then definitely you can understand how these formulas were derived and utilized to solve projectile problems. Now let us apply the formulas we have discussed a while ago. Make sure you understand them all and make a list of these formulas as we go along. Problem number 13. A motorcycle stunt rider rides off the edge of a cliff. Just at the edge his velocity is horizontal, with magnitude 9 meters per second. Find the motorcyclist's, letter A, position and letter B, velocity after 0.5 second. So list the given information. The initial velocity of the rider v sub I is 9 meters per second. Since the rider is a type 2 projectile, so his initial angle of flight is 0. We have also given time 0.5 seconds. For the required quantities, the problem requires us to solve for the horizontal and vertical positions, x sub f and y sub f. Also, the magnitude and direction of final velocity v sub f and theta sub f, respectively. Our preliminary solution is to find the x and y components of the initial velocity. We have mentioned earlier that this is a type 2 projectile. Therefore the x component of the initial velocity v sub ix is automatically 9 meters per second while its y component is 0. Then solving for the position at time 0.5 second. The horizontal position of the rider is x sub f equals the x component of the initial velocity times time t, that is 9 times 0.5, so the answer is 4.5 meters. For vertical position y sub f, we will use one of the freefall formula v sub I times t minus 1/2 gt squared. Substituting the values will give a vertical position of negative 1.23 meter. Remember, this negative sign indicates that the rider is located below the edge of the cliff at 0.5 second. Any questions so far? Can you keep up? Good. Now let's continue. For the magnitude and direction of final velocity, we solve first the x and y components of final velocity. We know that the x component of velocity is constant, so v sub fx is also 9 meters per second, same as with the x component of the initial velocity. I guess no problem about that. For the y component v sub fy, we use another freefall formula, y component of the initial velocity minus gt. If we substitute the given information, then v sub fy is negative 4.9 meters per second. Now, the next step would be the magnitude of final velocity v sub f. So we use Pythagorean theorem formula, square root of the quantity v sub fx squared plus v sub fy squared. Pressing on the calculator will give 10.25 meters per second. For the directions a to sub f, inverse tangent of v sub fy over v sub fx, so it is negative 28.57 degrees. Hence, 0.5s later, the rider moves at a velocity of 10.25 meters per second, 28.57 degrees below positive x-axis. Another two-dimensional motion that we are going to study for today is uniform circular motion. A car moving of circular track with constant radius at constant speed, a communicating satellite orbiting the Earth, and a skater in a circle with constant speed are some examples of this type of motion. Uniform circular motion is a type of motion when a body moves in circular path with constant speed v, that is, the magnitude of the velocity is not changing. However, in order for a body to turn around the circular path, the direction of this velocity is continuously changing. This change in direction corresponds to acceleration called centripetal acceleration a sub c, that compels the body from straight line motion into circular motion. In next section, we will discuss the kinematic quantities and equations for this type of motion. Now I will discuss to you the kinematic quantities and equations for uniform circular motion. Imagine a car moving at constant speed on a circular track of radius r. We call this speed as linear speed, denoted by letter v. It is the distance traveled by the body in one revolution along the circular path in a given period of time t. This is also the magnitude of instantaneous velocity of the body, provided that the motion remains uniform. For this reason, we use the letter v instead of s for the linear speed. The distance traveled by an object to complete one revolution along a circular path with radius r is equal to the circumference of that circle 2 pi r, and the time it takes to make one revolution is called the period t, hence linear speed v is expressed as 2 pi r divided by t. Although the magnitude of the linear velocity is not changing, its direction is continuously changing as the object turns around the circular path. This change in direction of the linear velocity corresponds to an acceleration called centripetal acceleration, or sometimes it is called radial acceleration. Centripetal acceleration, denoted by a sub c, is the instantaneous acceleration that compels a body to move around a circular path. The word centripetal means seeking the center. Therefore, the direction of centripetal acceleration is always towards the center of rotation. Centripetal acceleration can be computed by dividing the square of linear speed v by the radius of the circular path. Another formula can be derived by substituting 2 pi r over t to v, so centripetal acceleration is also equal to 4 pi squared times r divided by the square of the period t. Wow! We've gone this far. This is the last problem I'm going to explain for this unit. Problem number 14. In a carnival ride, the passengers travel at constant speed in a circular path of radius 5 meters. They make one complete revolution in 4 seconds. Letter A. What is the linear speed of this ride? Letter B. What is their acceleration? As mentioned in the problem, the radius r is 5 meters and the period t is 4 seconds. Required quantities are linear speed v and centripetal acceleration of sub c. So here's the solution. For linear speed v, using the formula 2 pi r divided by period t, so the linear speed of this carnival ride is 7.85 meters per second. For centripetal acceleration, that is 4 pi squared r divided by t squared, substituting the values will give an acceleration of 12.3 meters per second squared. Now, give a meaning to these quantities. Maybe you are thinking, what causes dizziness when you are on any carnival ride? One easy way is to compare the centripetal acceleration to value of gravitational acceleration, which is 9.8 meters per second squared. Since our answer, 12.3 meters per second squared, is greater than g, therefore we can presume that this ride is a dizzy one. More frightening than you are falling due to gravity.